Hey everyone, how are you doing? So let's look at another competitive style programming question, a Leetcode style question. And the topic we'll be looking at today is something called two pointers. It's a technique to solve problems, and specifically, we will look at a subcategory of two pointers technique called relative motion. So we will look at a couple of solutions, and later we will optimize. The second solution will be optimized for this question, and we'll also understand the reasoning behind this relative motion and how we can think of it intuitively. So, without further delay, let's get started with that. So, this is our agenda for today. So, we'll look at the problem statement and clarification of what is expected, and then we will solve the problem in a linear space, complexity, and time complexity. And then we will optimize the solution using a two-pointer technique. And specifically, we'll look at relative motion and understand what it is and how it works intuitively. So we will code that optimized solution. And then we will look at the difference in asymptotic thing, like when we talk about asymptotic notation, that versus reality, like how it compares. So this is our agenda for this video. So let's look at the problem and the expected output. So what we have here is an input object which has two keys like data and next. And the next in turn contains another object with data and next, and it like iteratively nested. Uh, and then ultimately we reach the end where there is no next key in the nested data. So this is the input. And the question is we have to get the last n number. So in this method, what it accepts is the list, which is the input object, and it also accepts a number n. So when given an n, the method should return the last n numbers as an array. For example, if n is 2, then it should return an array containing 45 and 25 because these are the last two digits here. So let's look at some test cases here. So like I mentioned, if n is 2, then it would be 45, 25. When n is 1, 25 is the last number, so it should return that. There are two special cases that we need to handle, which is like if n is greater than the length of the list, then it should return the entire list. So here 20, which would return everything, 12, 23, 45, 25. So that is what is going on here. And if n is 0, then it should return an empty array. So this is the question and the expected output. So we can think of this, the given input as a linked list, right? Because it has a data node and then the next pointer pointing to the next data node and so on until there is a null terminator. In our example, the key will be missing, which is the next key will not be present, but we can visualize it this way so that it makes it easier for us to solve the problem. So let's start solving this problem in a linear fashion. So first thing what we have is like the linked list, right? Uh, to get the last one, it with the current structure, it's a bit difficult because let's look at this linked list. The pointers are only in forward direction, like from the head to the tail. We don't have it in the opposite direction. Like this is not a doubly linked list; it's a singly linked list. So going from the backwards is difficult with this structure. So what we can do is create a linear structure that will enable us to do that traversal. So what do I mean by that? Is to create an array and store the data in a linear fashion from the linked list. So I'll just traverse through the array until I reach the null terminal, and I'll keep pushing the data into the array. And yeah, so I'll map the data to next, and yeah, I'll just keep on doing this iteration. And then if n is greater than 0, I'll slice the array from the behind or else I'll return an empty thing. Now let's run the tests for it and see if our solution works. Yeah, it seems to work because for the last two we have 45 and 25. Yeah, that's the last two digits. And then for the last one we have 25, and when it's greater than 20 we get the entire list, and we get an empty array when it's zero. So this works. Space complexity of the solution is linear O of n because we store every value from the data node in the linked list into this array. Let's try to optimize that. To optimize the space used by the algorithm, we will use the two-pointer technique. So as an analogy for the relative motion, like to understand the intuition behind the relative motion, let's consider two people who are to walk down a square, like a path filled with squares. And one person is going to take the lead and the other person is going to follow. So the color red would take the lead and the color black would follow. So let's look at it this way. So now we have a, a point called n in the path, like the this entire path of squares. There's a point called n, which is somewhere down the line in the path of squares. So let's move our leader to the square n. And once we have our leader at square n, we can start moving both the leader and the follower one square at a time. So what we can do is let's move the follower to the first square. Yeah, so let's move the follower to the first square and the leader by one square. Again, let's move the follower one more square and the leader another square, and we do it one more time and another time, and we continue to do this until the leader finishes the entire square path. So by this iteration the leader has completed the square path, but we can also see that the follower has reached n. So when the leader completes the square, the distance between the follower and the finishing line is basically n. So this is the relative motion that we will be using. This intuition is what we'll be using to design our two-pointer solution to save space. So let's get into the actual algorithm. So let's clean up this linear space solution, and let me create two pointers, leading pointer and lagging pointer, and I'll assign both to the list initially. And then I'll also assign a variable called counter to keep track of the steps. Let's implement the first step of the algorithm, which is to move the leading pointer n steps ahead. We could do that by checking if the counter is lesser than n and if we still have the leading pointer. And if that's the case, then we will keep moving on by pointing it to the dot next method and increase the counter. The next step is to move both the leading and lagging pointers one step at a time until the leading pointer reaches the end of the sequence. And how we would know that the leading pointer has reached the end is if it becomes undefined, right? So until that's not the case, we step up the lagging pointer and also the leading pointer. As we saw in the analogy, by this point we know that the lagging pointer is just n steps away from the end of the sequence, right? So we can keep uh, iterating and moving the lagging pointer forward and collecting the data into the result array, and then return that result array later. So by this way, we would have got the last n data points from the given object. So let's just implement that in this way and finally return the result array. Let's quickly run the test to see if our solution works. Yeah, it seems to work. The last two digits is 45, 25. Let's check with the actual data. And yeah, so the last two digits are 45 and 25. Last is 25, and then we get that entire object entry if it's greater than, and then greater than the list, and then an empty array if it's zero. So this still works. So that's how we have optimized the space. We cannot do much about the time complexity because we have to go linear. So linear is the best we could do in case of time, but in space of when it comes to the space complexity, we have optimized it. This is where something that we have to note about the asymptotic. In the asymptotic notation, the space complexity is still O of n because it's like O of the length of the sequence, which is n minus some arbitrary number, right? When we subtract something, we usually ignore it in the asymptotic. So it's still O of n asymptotic, but in practice, we have got a better space utility for with this algorithm. Like instead of storing the entire list, we now just store only the last n sequences of it whenever we do that. The worst case would still be O of n though. Yeah. So that's it for today. I'll see you in the next video. Have a good day then. Bye.